right, we're gonna go ahead and jump in. And on the syllabus, we're gonna talk. It's the next topic is asymmetric catalysis. So we're gonna talk about that today, and then and Wednesday, and then on Friday we'll do. Hold up, we were supposed to be doing those papers today, weren't we? With the frustrated lone pairs. Now, let's just do that Friday, and then we'll do this today and Wednesday. All right. Um, So yeah, just hold on to those, and then we'll do those on Friday. So we're talking about today how to induce chirality, right? There's a couple of ways to do that. Man, I just been
Okay.
talking about this with my 9 o'clock class. So one way to do it is if you remember from organic two, whenever you took it, uh, one way to do it is to take a chiral substrate and react it with something that's achiral so you can get an unequal mixture of stereoisomers. And then, but there's a more advanced ways of doing it too, and namely using chiral catalyst, or you can also use like kinetic resolution things. So that's what we're going to talk about today. So we're going to talk about catalysis, organocatalysis, and then resolution as ways to induce chirality. And then we're going to look at some stereoselective reactions and some of the more uh, famous stereoselective reactions we're going to look at. Uh, and we're going to talk about chirality as a concept. So, uh, chirality is basically a property, right? You remember this from organic one where you had to figure out whether something was R or S, where you have a chiral center on a molecule, and what if that center was non-symmetrical, sp3 hybridized, and the mirror images overlapped, I mean, didn't overlap or was non-superimposable, then we called it chiral. There's a fourth criteria for chirality as well, and that is that you have four different substituents. But all of that is connected to being non-symmetrical, being sp3 hybridized. All right, and then the mirror image of a chiral molecule is non-superimposable. So you take the image and the original image and the mirror image, and you try to overlap them. You can't, because the original image and the mirror image are exact opposites of one another. So if you have your original image is R, then your mirror image is going to be S, right? And this is dealing with what we call enantiomers, those non-superimposable mirror images. We call them enantiomers. But there are other types of chiral uh, species, like diastereomers, where you have two chiral centers, but the diastereomer is not a mirror image, right? So if something is RR, like you got two chiral centers, and the two chiral centers are RR, then the diastereomer of that would be RS, and the enantiomer would be SS. All right. Um, so when you think about chirality and why it's important, uh, when you talk about synthesizing chiral molecules, basically, like the majority of your natural products, the majority of your medicinal targets, the majority of your drug targets contain chiral centers, right? It's just a fact. And the way those chiral centers are oriented matters. If you have a molecule like Prozac, it has a chiral center in it, and if you take the isomer of Prozac, it's not effective for what it's supposed to do, which is to help with depression. Uh, so this is a huge part of organic. It's a huge part of organic synthesis, and is probably one of the more important topics, and the most one of the more studied topics, because again, this area affects, like, it really affects the entire drug industry, being able to synthesize molecules with chiral centers. As a matter of fact, I'm gonna take a pause right here just to give you an example of what I'm talking about. Uh, I need to do a new share. So let me show you. So think about a molecule like this, right? Like Taxol. This is Taxol. Taxol has multiple chiral centers, and all of these chiral centers, if you make now if you extract this from its natural source, which is the Pacific yew tree, from the bark of it, the bark of the Pacific yew tree, if you extract it from its natural source, you're only going to get maybe a milligram. I think it's something like you can cut down like 100 yew trees, and you're only going to get like maybe a gram of paclitaxel from the yew tree, right? So and this is a Taxol. The reason why I'm saying that is because Taxol is a chemotherapeutic, right? It's one of the frontline drugs for treating cancer patients. Uh, but you don't have enough yew trees. You can't harvest enough yew trees to get enough paclitaxel to give to a patient, or to one patient, let alone millions of patients who are dealing with cancer. So you had to have a way to synthesize it, right? And so there were basically in the 90s, late 80s, early 90s, there were two groups kind of competing to make this thing. One group was in Casey Nicolau's group, and then the other group was a researcher down at Florida State, Robert Holtman, who ended up selling his synthetic pathway to, if I'm not mistaken, he sold it to Bristol Myers, and he licensed it to them. So he still gets royalties off of that. But the point is, like, all of these chiral centers have to be set in this molecule, and they got to be set the right way, because the way that Taxol binds to whatever receptor it binds to in the cancer cell, if any one of these stereo centers is off, or it's not the right configuration, it's not going to bind properly, right? So you can see here where you have, let's say this is dashed. I mean, it's wedged and not dashed. Then it's gonna limit the effectiveness of the drug, because it won't be able to bind properly to that receptor, right? By the same token, if any of these are different, then it's probably going to have an effect on how well this drug binds and how well it's taken up into the cell, so on and so forth, right? So that's why when we talk about asymmetric catalysis, that's why it's so important to be able to do it, because a lot of your drugs, and a lot of, especially your chemotherapeutics, a lot of them have natural product origins, or they're analogs of natural products. So if you can't synthesize them in large amounts with the proper stereochemistry, then it's kind of useless to have them. All right, so that's why this is such an important topic. All right, so the goal of asymmetric catalysis is single enantiomer synthesis, right? Where you take two achiral species, you react them together, and then you get one enantiomer, either all R or all S or whatever. Right? That's always the goal. But you normally end up with a mixture, right? Either a mixture of enantiomers or a mixture of diastereomers. Um, but the goal is always to generate one isomer in a higher amount than the other, right? So you wanna favor one enantiomer or one diastereomer over the other, and that's what we call asymmetric induction, right? So when you're doing asymmetric synthesis, again, there's a couple of ways you could do that. You could start out with something that's chiral, and then add it to something that's achiral, and you can get an unequal mixture. Uh, but most of the time, the most efficient way to do it um, is to do what we call asymmetric catalysis, which we're gonna talk about shortly. All right. So let's just talk about a couple of terms first before we jump into the actual meat. So we have this value, what we call enantiomeric excess, right? You can calculate the basically the ratio of one isomer to the other. Uh, and the way you calculate that is you use some type of chromatographic method. You use gas chromatography, HPLC, supercritical fluid chromatography, something in that area where you can actually and your instrument has to have a column, a chiral column on it that causes some differentiation between the enantiomers, right? So they come out at different times, different retention times, so on and so forth. Did y'all study GC and HPLC and all that when you took advanced instrumental?
Yeah, we briefly covered it.
Okay. So when you use a GC with your gas as your carrier, or LC with some solvent mixture as your carrier, you basically have what's called a chiral column. So the column has some type of chirality built into the stationary phase, and so as the chiral molecules pass over, one enantiomer may interact more with that stationary phase than the other, and so you get kind of separation between those enantiomers. Now you can't separate enantiomers by flash chromatography. You can separate diastereomers by flash chromatography, but not enantiomers. All right, so the enantiomeric excess is basically the ratio. So if you get a reaction that's 89% EE, that means that the ratio of one isomer to the other out of 100 is basically 94.5 to 5.5. So when you subtract those two out, uh, you get 89% EE, right? And the way to calculate it is that little equation at the bottom, R minus S over R plus S times 100, right? So it'd be 89% for this particular reaction. So that's important to be able to calculate that because that's how you know how efficient your catalyst is and how good it is at creating a bias in the transition state to give you one enantiomer or one stereoisomer over the other, right? So again, just kind of just repeating what I just said, right? You the way you get asymmetric induction is either have a bias in the transition state, right? If you have a bias in the transition state, if it's a competitive process and you have a bias in the transition state, then you're going to get an unequal mixture of stereoisomers. If there's no bias, then you're going to get a racemic mixture. So if you take, for instance, the little example shown on the left over here, right? If the for the last reaction that we were looking at, you can see here is just a Michael addition, right? So you add in a cuprate, you do a Michael addition at the uh, beta carbon, right? And these are your two enantiomers, right? So here, if the methyl group attacks the top face, is going to give you um, the S enantiomer. If it attacks the bottom face, it's going to give you the R enantiomer. But the thing is, when you look at something uh, like this, it's saying that it's giving you 89% EE for the S enantiomer, right? But so there must be something here in the reagents that's giving you your transition state bias. So we're gonna talk about that later. But you have a bias, and you have to have a bias in the transition state so that you got two competing processes, and one of them is going to be energetically more favorable than the other. So you can also do this by resolution, right? So you take both enantiomers, you put them through a process, and if the process is specific for one over the other, then you can uh, resolve that mixture and enrich it in one enantiomer, and then the other enantiomer ends up getting, tossed. That's the drawback of doing resolution, is that you end up losing one of your enantiomers or one of your compounds, which is it may seem trivial, but if you build up like a big uh, like a huge scaffold, right? A huge molecule or a huge fragment that you're using in a total synthesis, and you end up with two stereoisomers, and you only want one. You know, you put it through this process, and it's specific for that one. You end up tossing the other one, which is kind of wasteful, right? It's not atom economical. So resolution has its drawbacks, but it's also really efficient. Like you can, it's a foolproof method, and we're going to talk about that later on. So you can have start with a racemic mixture and resolve that enantiomer from that mixture and enrich, you know, the product in one stereoisomer, whereas the other one just kind of gets left behind. So one of the main ways to induce chirality and create bias in the transition state is to use a catalyst, a chiral catalyst, right? There's a couple of things that you need here, right? You need a transit. Most of the time, it's going to be a Lewis acid, like a transition metal. So you need a transition metal that can be multivalent, right? So you need to be able to bind your substrate and coordinate to that catalyst. You also need something around that catalyst, like a ligand, and I think y'all probably have talked about this already. If you taken 513, uh, you need a ligand bound to the catalyst, right? And there are a lot of different types of ligands. The one that I have shown here over on the left is called. This is the reason I'm showing this is because it's one of the more popular ligands for asymmetric catalysis. It's called a bisoxazoline ligand, a box ligand, and it's easy to make. Uh, it's cheap and it works, right? Especially if it's substituted with like those tert butyl groups, it works. It creates a pocket around the catalyst, uh, and your substrate is bound to the catalyst. And so anything that's attacking that substrate is trying to it is going to attack from the pathway that's lowest in energy, right? And that's the most efficient, right? So you still end up more than likely you still end up getting um, you still end up getting two products because it is a competition. But based on what the substituents are on the ligand, that's going to determine how much of one product you get over the other, right? Because again, you have to be able to create a bias in the transition state so that you got a competitive process happening. And one of those processes is a little bit lower in energy than the other, right? So you put a chiral ligand on a transition metal, and boom. I mean, uh, this is probably the most applied method for doing for synthesizing chiral molecules is to use asymmetric catalysis. That's a lot of catalysts, a lot of different reactions that they apply to, and so yeah. So again, the box ligand is one, and this ligand is what we call C2 symmetric, right? You can put a line of symmetry here. Hopefully you can see my cursor. You can put a line of symmetry here through here and rotate around it, and that you're going to get the same thing on both sides if you rotate around it. So this is wedged over here. If you rotate it around the line of symmetry here, it would be dashed on that side, and this will become wedged, right? So uh, there are other types of chiral ligands. There's you have C1 symmetric ligands, where one side has chirality and the other side doesn't. I don't know if I got an example of that in here, but I can show you real quick because the false ligand is a good example of that. See, oh, here we go, right here. Perfect. All right. Is that? Can y'all see my screen, my internet screen?
All I see is your face.
Okay, that's bad. Let me give you something better to look at. 'Cause my face is not worth looking at.
I think,
All right. So something. Can you see it now?
yes.
Yeah. So this ligand right here. This is a a ligand that was developed by Andreas Faults, and it's called a Fox ligand, right? So you have the box part on one side, right, and then you have a diphenylphosphine group on the other side. And the thing about this, and Faults, these ligands that he developed are very, very, very efficient, and they're very good at what they do. Uh, so again, the coordination to the metal that comes through here, right? The phosphorus and the nitrogen, they both have lone pairs. They can both bind to the metal and basically chelate. Like if you learn that term in advanced inorganic, then I'm sure you know what that means, right? It means like it comes from the word a Greek. I think it's from a Greek word that means claw. So the ligand kind of grabs onto the metal. So this is what you would call a C1 symmetric ligand, right? There's no plane of symmetry, right? So you got a box group on this side, and then this group is on this side. But the ligand works. I mean, these false ligands are very, very good for a lot of like an array of different reactions. All right. So you have C2 symmetric, C1 symmetric, uh, and let me go back to here. All right. All right. So again, the goal is to create bias in the transition state. So that's the goal, right? So let's look at one of the probably one of the most famous asymmetric catalysis reactions in the history of organic chemistry. And this was Sharpless asymmetric epoxidation. This is done by Barry Sharpless. I think he's at, I want to say he is at Cal Berkeley. Uh, I may be wrong about that, but I think he's at Cal Berkeley. Uh, world-renowned scientist, world-renowned chemist for the development of this asymmetric catalyst for epoxidation, right? And so, and it's tunable, is what we call tunable. You can change the diethyl tartrate. That's what the DET is. You can change the chirality on that, and uh, that alone can determine which one of these two isomers you get, right? So you have, uh, and this works, right? Let me also specify this. Like a lot of times when these systems are developed, like you want to develop a system for epoxidation or you want to develop a system for hydrogenation, right? These systems are developed on specific substrates. So this asymmetric epoxidation was developed for allylic alcohols, right? So you have an allylic alcohol, and then you're going to treat it with this set of reagents: butyl hydrogen peroxide, titanium tetraisopropoxide, and then molecular seals, right? That's molecular seals are just like they're a drying agent. So they're like little beads, ceramic beads. Put them in the oven, activate them, put them in your reaction, and they actually absorb water from the reaction. All right. So these are the conditions for sharpless asymmetric epoxidation. A lot of times too, you'll see these reactions done at low temperature, right? There's a reason for that. The lower the temperature, the more selective the reaction is going to be, because at low temperature, there's less energy for other processes to happen, right? So the lower your temperature is in a specific reaction, the more selective that reaction is going to be. So if you can see here, you can favor one enantiomer of epoxide over the other, depending on the diethyl tartrate ligand that you use. If you use the minus diethyl tartrate, and minus plus and minus is just dealing with the optical rotation, right? We don't really use that anymore, but here, they use it to specify which diethyl tartrate ligand is being used. So minus diethyl tartrate, plus diethyl tartrate, and you can get either one of those isomers, right? In high yields, and also almost 99%. I think it's like 99% EE. So with minus dialpha tartrate, you get that top epoxide 99% EE, right? So basically, the ratio basically 100 to 1, right? Uh, and then with the bottom isomer, same thing, right? It just depends on which one you want. And the reason why this is important, again, those epoxides are precursors to other molecules, right? You could take the epoxide and you can react it with some nucleophile and pop it open, or maybe your what you're synthesizing calls for an epoxide in the product, right? So this is what the transition state looks like for uh, the sharpless asymmetric epoxidation. So first of all, it's bimetallic, right? So you have two titaniums involved in the transition state. This is your allylic alcohol bound to one titanium, and then your hydrogen peroxide, your not hydrogen, butyl hydrogen peroxide, which is here, is also bound to titanium. So this is where your oxygen is going to be transferred from to your alkene to do the epoxidation. Uh, and the thing about this is the reason why the selectivity is so high is because the um, alcohol can only chelate at a specific location, right? It can't you won't find the alcohol chelated to that titanium that's shown, and then find in another instance find it chelated over here, right? It's very selective about how the alcohol binds to titanium, and depending on which isomer of diethyl tartrate you use, that's going to determine how your oxidant, which face your oxidant transfers oxygen to on your alkene. All right. So again, it's a bimetallic transition state. You can see the architecture. You can see how the DET, that's this part right here, right? You can see how that forms like a pocket around titanium, and even on this side, right, where it's on the back side. And the isomer of DET is going to determine everything, right? But it's a very selective reaction, and it is highly efficient. You get great yields. The scope is really good. Like you can substitute your um, allylic alcohol with different substituents, and it still works, and it doesn't diminish the reactivity or the selectivity. All right, but that's where you when we talk about a bias in the transition state, these DET ligands create that bias, right? So that the allylic alcohol only binds to one side, and then the oxygen is transferred to either the top face or the bottom face, depending on what the DET structure is, like what which isomer of DET is being used. All right, any questions about that? It's fascinating the fact that you can take these diethyl tartrate ligands and attach them to a metal and get this epoxidation to go in high yields and like basically 100% or 99% EE. It's very fascinating that you're able to do that. But this is again one of the pioneers in asymmetric catalysis. Uh, and this is a application, right? So it's this lolamide molecule, which you can see right here. You can see here, you actually have an epoxide, in your product, right? And so, if you look at the precursor to the final product, the lolamide, you can see they use diisopropyl tartrate, excuse me, here, and titanium isopropoxide, and then tert-butyl hydrogen peroxide, again at minus 20, and methylene chloride, right? And you can see here you got an allylic alcohol here, you got one here, and you have an alpha beta unsaturated ketone, which is almost the same structure, right? Here, but that doesn't get epoxidized. Only this allylic alcohol gets epoxidized right here, right? Even this one doesn't. Now, I'm not certain as to why they propose why this allylic alcohol gets epoxidized and this one doesn't. Uh, but that's the results, right? you epoxidize over this allylic alcohol over this one, and then this alpha beta unsaturated ketone doesn't even get touched, even though that alkene is there, and then this alkene doesn't get touched either. So this is highly selective for allylic alcohols, and it's even highly selective for the type of allylic alcohols that you see that you're able to epoxidize, and is regioselective, right? So you have, again, here's an allylic alcohol motif right here. Here you have another allylic alcohol motif, and here you have just a alkene, and this is regioselective. It doesn't touch that alkene. It has, you have to have the allylic alcohol to help that alkene to be able to chelate to the metal, right? It doesn't chelate without that. You can see here 99% EE, 87% yield. That's like the holy grail of asymmetric catalysis, to get 99% EE and a yield that's over 75%, right? That's like, again, that's a goal. That's the goal of every reaction that's done through asymmetric catalysis. 99% EE, high yield, and very low catalyst loading, right? 1 to 2% catalyst. If you meet those criteria, then that reaction is going to get adopted. Like if you're developing a reaction, if it is low catalyst loading, high yield, and high enantiomer selectivity, everybody's going to use it. All right. How much time we got left? Take a few minutes. So the another really important reaction in the area of asymmetric catalysis is the aldol reaction, right? If you remember, if you took even if you took my class for organic 2 lab, when we were making chalcones, that's what we were doing. We were doing aldol condensation between aldehydes, and so we started out with like aldehyde and a ketone, and we did an aldol condensation. We started out with like acetophenone and then benzaldehyde or something like that, and we made those chalcones uh, with these type of structures right here. So we did aldol condensation, but the chirality um, comes in here when you do the aldol addition, right, where it doesn't condense, but you make a beta hydroxy ketone. And those are important synthetic intermediates, like really, really important, because you can do a lot with both of those functional groups, with the alcohol or the ketone. So one of the first examples of this of the aldol being using like asymmetric catalysis or synthesizing the beta hydroxy ketone with the OH group as a stereo center was done by Mukiyama. And you can see the date on that, 1973, long time ago. But this reaction is one of the more famous aldol reactions known to organic chemists. And not only that, it's also an extremely useful reaction because it's the scope of the reaction is so broad that you could basically take any aldehyde and react it with one of these Mukiyama enolates, and it works, right? It's a great reaction. So you can see the metal, titanium tetrachloride. This is not asymmetric, by the way. I'm gonna show you the asymmetric aldol on the next page, but you take titanium tetrachloride and an aldehyde. So this is your catalyst, and then you take this what's called a silyl enol ether, the silyl part for the TMS group here, the enol part for the enol motif right here. The ene is the double bond, all is the oxygen. So it's called a silyl enol ether. And then with that, if you react that with an aldehyde, you can get out this TMS protected beta hydroxy ketone, right? So the silyl enol ether, you make it from here. You start with a ketone, treat it with a base, you get the enolate, and then you just trap it with TMS chloride, right? When we talked about those protecting groups, TMS chloride, TBS chloride, TBDPS, all of those different groups like that. If you take that enolate right here and react it with TMS chloride before you react it with an aldehyde, it's going to get protected. Right, so that's how you get the silo ether, and then the ketene acetal, which is here, is similar, but instead of starting with a ketone and making an enolate, you start with an ester. So you will start with an ester, and then enolize that to get the enolate, and then trap it. All right. So again, ketene acetal. So now you got a beta hydroxy ester derivative, which is again a powerful precursor because you can think about the ester group right here, what you can do with that, what you can convert it into, what you can add to it, uh, and it gives you a great precursor for like just building up more complicated architecture, like molecular architecture. All right. So when we talk about the aldol, it's important to understand like where the chirality is possible, where it comes from. So this is kind of a guide as to uh, what's possible with the aldol, because if you think about, if you have enolates that have substituents on them, like if you notice here, the enolate is unsubstituted at the alkene, right? Same here, no substitution here. But if you extend the substitution, right, then you have the potential to form what you call a E enolate or a Z enolate. E enolates are here, where this basically this is E, the stereochemistry of that alkene, where the oxygen is here, and then the other group is opposite to it. So it has an E uh, stereochemistry, and then the Z stereochemistry. You can see the oxygen and this group are on the same side, right? If you recall that from organic one, where we talked about alkene stereochemistry, it's either cis or trans or E or Z, right? So this is tri-substituted, so it's going to be either E or Z. Now that has ramifications, right? Because if you have a E or Z enolate, then you're going to produce products, right? Your products now have two stereo centers in them instead of one, right? So with the E or Z enolate, right, with the Z, the predominant product is what we call syn, right? Where both groups are on the same side. Like you can see both of these are wedged and both of these are dashed, right? That's with the Z enolate. And there is we're going to talk about this in a second, and then we'll probably wrap up and pick it up on Wednesday. But there's a definite a model to predict this, right? So and then with the E enolates, you get anti-aldol products, right? Where these are opposite. This is dashed and that's wedged, or this is wedged and that's dashed. It just depends on uh, what the conditions are, that which one of those is going to be, that determines which one of those is going to be favored, right? So the way that you control this is by your substrate, right? If you start out with an ester, then for esters, the predominant uh, enolate is E. If you start out with a ketone or amide, the predominant enolate is Z. So you can go into the reaction knowing, okay, if I have this, I'm going to have a Z enolate. I can expect syn products. If I have this, I'll have an E enolate, and I can expect anti products. And the question then becomes, which anti or which syn product is going to be favored? That's one question. The other question becomes, if I see something different, like if I start with something that I know is going to give me an E enolate, and I see syn products, then that's indicative of something being different in the transition state, which I'll show you in a second, right? So when you extend out that substitution on your enolate, then you start getting into being able to make uh, products that have now multiple serial centers, which again, very important. These are great precursors to, you think about natural products and think about the backbone of a natural product. It may have this type of motif where you have uh, a substitution pattern on the backbone that looks something like this, right? So if you can build those up efficiently and high natural selectivity, then that's great. Um, And then you also think about, when you think about this, you also uh, have the potential now to make diastereomers of these, right? So this, the diastereomer, these actually, if you look at these products down here, they are diastereomers of these two enantiomers. But we'll talk about that later. All right. So this is the model. This is how we predict like sin and anti, right? It's called the Zimmerman-Traxler model, and we use that to predict the outcome of an aldol reaction, right? So if you look at the model here, it was proposed is a six-member transition state, six-member chair transition state, chair-like transition state, where your metal organizes it. This is your enolate right here, and then this is your uh, aldehyde, right? And so your enolate and aldehyde are gonna uh, interact with one another such that the R group up here on your enolate doesn't have any steric interaction with the R group on your aldehyde, right? Because this is fixed. The Z enolate is fixed, but the approach of your aldehyde is not, right? So what's proposed is that the lowest energy pathway is here, where the hydrogen on the aldehyde is pointed here on the same side with the R group, and then the R group on your aldehyde is here. Yes, you're going to have some sterics here, but it wouldn't be as severe as having this R group and this R group on the same side, right? So this is the favorite Z enolate conformation, right? And then this is this favorite where your two R groups are here on the same side. Same thing here for the anti, right? This is an E enolate that's fixed, but the approach of your aldehyde isn't, right? So the hydrogen is going to prefer to be here where this R group is. And then the disfavorite model for the E is here, right? Where the two R groups are on the same side. All right. And so this model allows us to predict the stereochemical outcome of any aldol reaction. We can propose this model for many different types of aldol reactions, regardless of um, the catalyst and regardless of what type of um, enolate you're using, right? E or Z. Any questions about anything so far?
Not so far.
All right. Let me see what's next before. Yeah, I want to wait and do that. We're gonna stop here because I don't want to do the auxiliaries yet. Yeah, we'll wait because the chiral auxiliaries, that's the next topic, and it's a little bit different because you don't necessarily need a chiral. It's not a asymmetric catalysis. It does use a catalyst. Sometimes they use boron or some other catalyst, Lewis acid, but you don't need an asymmetric catalyst. You don't have a catalyst with a ligand on it. The chiral auxiliary is more of kind of like the first thing we talked about back at the beginning of the presentation. We talked about taking something chiral and adding it to something achiral. So we'll talk about that on Wednesday, and then Friday we're gonna do those papers that I sent. All right. Anybody
Okay.
got any questions about anything?